Welcome to the first video in a series on the xv6 operating system kernel. xv6 is a very short but very sweet Unix-like operating system that's used for educational purposes. If you want to understand how an operating system kernel works, then this is the video series for you. In this series, I'll walk through the code and explain in detail how a kernel works. You'll get to see the internal design of a real functioning operating system. In this first video, I'll introduce xv6. I'll list its features and go over the basic functionality of the system, telling you what its capabilities are. Then in subsequent videos, I'll be explaining how the kernel works. I'll describe the data structures and overall principles and organization, and I'll go over the code itself. A couple of years ago, I made a similar video series on xv6. What you're watching today is a complete and total remake of that series. The original series had 38 videos, and this series will be approximately the same size, which is an indication of the depth that I'll be going into. This series will cover the same material as the older series. I'm remaking the series for several reasons. First, there have been some changes to the xv6 code, and the older series is now a bit out of date on several key points. And second, I wanted to improve the quality of the video series. Nevertheless, this video series and the previous video series cover the same material in roughly the same order in roughly the same number of videos. So please be aware that there are two versions of the same material. Of course, you should watch this, the new series, and not the old series. I'll leave the old series online until I've completed the new series. So far I'm about halfway done, but by the time you see this, it'll likely be completed. Here are the questions that I'll be answering in this video. What exactly is xv6? Who is this video series for, and what background do you need in order to understand this material? What are the main features of xv6 and what can it do? What user programs and tools are included with the system? And what is xv6 missing? How has it been simplified from, say, Linux? And finally, what system calls does xv6 include? That's this video. In future videos, we'll see in complete detail how xv6 works. xv6 is an educational system developed at MIT. Its purpose is to teach how operating systems work, and it's used in operating system classes in a number of schools. It's not quite practical for production use, although I think you'll be surprised at how functional it actually is. xv6 runs on a 64-bit RISC-V computer. An earlier version was targeted at x86, but that version is now obsolete. Like any operating system, xv6 is designed to run on a bare machine. It doesn't require or depend on any other software. It's targeted to run standalone directly on RISC-V hardware. But the assumption is that you'll be running xv6 on your laptop using an emulator called QEMU. QEMU is a virtual machine capable of running RISC-V code that is otherwise intended to run on bare metal. QEMU takes care of the booting and simulates real hardware accurately, making it possible to run RISC-V code regardless of whatever laptop you're using. If you happen to have a spare RISC-V processor sitting around, I suppose you could run xv6 directly on your hardware if you wanted, and that would be an interesting project. xv6 is a multi-core kernel, and the QEMU software will emulate a multi-core system just fine. Typically, xv6 runs on an 8-core processor. xv6 is short and very sweet. It's only about 6,000 lines of code, and most of that is written in the C programming language, with about 300 lines written in assembly language. In this video series, I'm going to do a walkthrough of more or less all of the code, explaining everything as I go. The code is clean and quite well written, and is an example well worth studying. I've read and written a lot of C code, but I've picked up a few new coding techniques here myself. One reason to study xv6 is that it illustrates the basic concepts you'd learn in an operating system course. That's another good reason to study this code in detail. For this video series, I'll assume that you know the C programming language. I won't assume that you have any knowledge of RISC-V, but I will assume that you've had some assembly language coding for some other architecture. I'll walk through the RISC-V assembly instructions line by line, holding your hand, so don't worry. In fact, this series includes 3 videos that give a brief introduction and overview of RISC-V in case you know absolutely nothing about it. xv6 is meant to be compiled and run on a Unix-based system, so you'll need the basic toolchain with the C compiler, the make utility, and so on, as well as the QEMU emulator software. I compile and run xv6 on my Macintosh laptop, but you could also use just about any Linux system or run it under Windows using Windows Subsystem for Linux. Now, I'm guessing that you are currently in an operating systems class that is using xv6, but perhaps you're just interested in xv6 and kernel design. But in any case, I've taught OS classes, and I'll review some of the concepts as we encounter them, in case they're a bit new to you. In the rest of this video, I'll talk about the features that xv6 actually has, the system calls that it implements, and the features that are missing. I'll get into the meat of things in subsequent videos. I'm assuming that you're quite intelligent, that you're highly motivated to learn this material, and that you have the ability to focus for the amount of time that's required. This is going to be a fast-moving, academic-style course, so buckle your seatbelt. This video course is not for the faint of heart or someone just looking for light entertainment and a quick dopamine hit. It's designed to support someone taking a university-level course that uses xv6. Although these videos are long and detailed, I'm positive that you'll find some really cool material here. It'll take some work to understand it all, but believe me, it's really cool when you understand what's going on and how it works. By the way, if there are other students in your course, would you be kind enough to let them know this course is here? I make my videos for a couple of reasons. One is because I truly enjoy making them, and another is because I myself learn a lot about what I'm teaching. But the final reason is because I want to help random strangers. So, will you please let your classmates know this video series exists? Different students have different ways of learning, and perhaps there are others around you for whom my teaching style will work well. Now, let me list the main features of the xv6 operating system. It's got processes, and each process runs in its own virtual address space. To implement virtual memory, it uses page tables with one page table for each address space. There's a basic Unix-like file system with files and a hierarchy of directories. You can pipe data from one program to another program. xv6 is a multitasking kernel, so you can run many processes at once using time slicing. Furthermore, it's a multi-core kernel, so we'll see how several cores cooperate to schedule and execute programs concurrently. There are 21 system calls implemented by xv6. Production Unix and Linux systems have more like 300 or even 500 system calls. But these 21 system calls are the important ones. They provide the key functionality and demonstrate the core ideas of Unix and Linux. There are a number of user programs that are supplied with xv6 that illustrate the capabilities of this operating system. xv6 can run a simple shell program, which provides a command line interface with file redirection, pipes, and with the ability to run processes in the background. Several common Unix programs are provided, and you're probably familiar with most of these. cat copies files. Echo is used to print command line arguments. grep searches a file given a pattern to look for. Kill is used to terminate a process. The ln or link command is used to create a hard link to a file, creating a new directory entry. The ls command lists out the contents of a directory. The make directory command is used to create new directories. And remove, or rm, is used to remove links and remove files from directories. And wc, or word count, is used for counting the characters and words and lines in a file. All in all, xv6 can be considered to be a true Unix operating system, although it's definitely stripped down and minimal. So what's missing? There's a lot missing. Thankfully, all the complexity of a real operating system is just not there. With a real operating system, like Linux, you might be looking at 10 million lines of code for the kernel, and maybe another 20 million lines of code for device drivers. And that's way, way too much for any human brain to comprehend, or to read, or to understand. So, if you actually want to read and understand kernel code, xv6 is definitely the one you want to look at. So what's missing compared to a real Unix or Linux system? With xv6, every process has only one thread, while real kernels support multiple threads per address space. There are no user IDs and no login sequence. There are no protection bits associated with files, and in short, there is simply no security. The mount command is not available, so we just have one file system. In a real system, the virtual address space can be paged out to disk, so you can run more processes than will fit into physical memory at once. Paging is not implemented in xv6. There's no support for networks, no sockets, or anything like that. Although we have pipes, there's no way for processes to communicate or synchronize among themselves. xv6 supports device drivers, but it only has two very rudimentary device drivers. A production operating system is going to have many, many more device drivers to support all kinds of different hardware. And lastly, there's a very small amount of user code. I listed the 10 user-level programs that are distributed with xv6, but a real operating system would come with a whole lot more user-level code. Next, I want to list the system calls that are supported. I'll go over these in much greater detail later on when we encounter them, but I wanted to list them now just so you can see what xv6 has. These should be familiar to any programmer, and they're present in all Linux and Unix-based systems. In a couple of cases, the arguments have been simplified a bit, but these functions are basically the same functions that have been in Unix since the beginning of time. Fork is used to create a new process. Wait is used to wait for a child process to terminate. Exit is for terminating the current process. Pipe is for creating a pipe, which is a communication channel for sending bytes from one process to another. And we've got open, close, read, and write for dealing with files. We've got kill to terminate a process, given its process ID. And here's exec, which is passed the name of some executable file. It'll create a new virtual address space, then read in that file, loading it into memory, and then begin executing it. The second parameter is used to pass command line arguments to the new program. The make node system call is used to set up a new device, providing the name to give the device, as well as two numbers giving information about which device driver to use for it. Unlink is used to delete files. It'll remove a file from a directory, and if this is the last link to the file, it'll remove the file as well and reclaim the space that it was occupying. fstat is used to retrieve information about a file. Link is used to create an entry in a directory to an existing file. make dir, or make directory, is used to create a new directory. There's a notion of the current working directory, and we can change directories with change dir. And dupe is used for copying file descriptors. And each process has a unique process ID, and we can get a process's ID with getPID. Each process's virtual address space has a heap. We can use this system call to enlarge or shrink a process's heap region by moving its so-called breakpoint. We can put a process to sleep for a while with pause. In Unix and Linux, this is done with a system call named sleep, but xv6 uses the name pause for this functionality, presumably to avoid confusion with an internal kernel function, which is also named sleep. And with uptime, we can see how long the kernel has been running. Both pause and uptime work in terms of ticks since startup, not seconds or real time. In the next videos in this series, I'll be going through the code in quite a bit more detail, but I just wanted to start by giving you an idea of what the xv6 operating system kernel is, what features it has, and what its capabilities are. As I said, this series is not for the faint of heart. It's not for amateurs. It's for people who really want to look at an operating system kernel in detail. And again, if you are in a course using xv6, would you please let your fellow students know that this playlist exists, since I'm not exactly expecting it to go viral. Okay, with that said, let's get started on the next video. Thanks for watching, and I'll see you there.